Hi everyone. Today I'm going to be explaining how to evaluate complex contour integrals in 10 minutes. So let's get started. First, I'm going to be doing a contour integral. So what you should be familiar with beforehand is the polar representation of complex numbers, so r e to the I theta. You should be familiar with the concepts of a residue in the pole, as well as the Cauchy integral formula. And you should be familiar with calculus through multivariable, just for the basics of how to integrate some of the stuff we're going to be doing. So this is a problem I had to do, and I thought it was very instructive when I saw the solution. So I thought I'll introduce it to you guys, and hopefully it will be instructive as well. So we want to find the integral of this thing, this function of x from 0 to infinity integrated. We're calling that I. The integral is I. And they told us the integral is this already, which is convenient, very nice of them. But we're going to pretend like we don't know this. Just some real number, you know? So what's going on here? Well, basically, you have this function here. And you notice that if you integrate this on the real axis, that's the same thing as the integral you want to evaluate, right? So what we're going to do is we're going to create this contour. And we have to have this branch cut here because we have this log. They use log. I like to use ln, but same thing. So log of z causes a branch cut on the real axis because as you go around by 2 pi, then you've added a factor of 2 pi to your argument. And then you're going to go into another Riemann sheet. And so we need to have a branch cut at the real axis. So we have this contour. We want to avoid the branch cut, so we kind of go around it like this. This integral is going to be, this integral of f of z, dz, is going to be equal to the I. This is going to be used to close it, and this is going to be used to close it as well. And this one's going to be something else as well. So we're going to use the residue theorem, the Cauchy integral formula, that says that the integral over the entire region, the sum of these four regional integrals, is going to be equal to 2 pi I times the sum of these residues at I and minus I from the denominator. You can see these are simple poles of order 1. So first, we note that the integral over C3 is 0. And I should say we evaluate the integral. So we evaluate this integral. We use z equals r e to the I theta as r goes to 0. Because this is supposed to be infinitely small. It's supposed to be infinitely large. Because we are free to make that decision. That helps us evaluate these functions. So we're integrating over theta. Well, we're integrating f of z dz, but we translate that into an integral over theta. So dz becomes ri e to the I theta d theta. We just plug in z equals r e to the I theta. We get that here. And we take the limit as r goes to 0. We integrate from 2 pi to 0 because integral is going this way. So this integral is actually not that hard to evaluate in the limit because we can use log properties to separate this thing here. So the term with the e to the I theta, the sum of the two logs, this term will be 0 because this limit, in the limit as r goes to 0, this denominator is 1. You just have like r to the 3 halves, r goes to 0, this is 0. So the other term, you have to evaluate this limit, the limit of r to the 3 halves ln of r as r goes to 0. And then you can rewrite it in this way because then you get negative infinity for this and you get infinity for this. And then you can use L'Hopital's rule, take the derivative, 1 over r, negative 3r to the 5 halves over 2, negative 5 halves. This comes back up, and you see that the limit is 0, right? Because it's r to the 3 halves, r goes to 0, so it's 0. So the whole integral over C3 is 0. The integral over C4, the big circle, is also 0. We use something called Jordan's first lemma, but we can really see what's going on here if we look at this integral. This is like the same integral we're doing here, except that r is infinity instead of 0. And, the point is, if this is like an r that we got, this theorem says that z f of z, and the limit as z goes to infinity, should be 0. But really what's going on is that this z, this r, is standing in for the z in this case, because we're not really caring about these factors that don't impact the magnitude too much. That's where the theorem comes in, but the intuition is that we have this function of z, and we're multiplying it by another z. And if that goes to 0, this integrand is 0, so the integral itself is also 0. Only applies to the big circles, of course. So we look at this, that's the justification for why this theorem is true, sort of. We look at this limit, it's z root z ln z, ln is ln, over 1 plus z squared. And you see that this numerator is less than z squared. So this limit must be 0. Because, ln of z in the large z limit is less than the root of z. And this would have to be root of z for this to not be 0. So comparison test, this limit is 0, the integral is 0. Cool. So the two remaining integrals, c1 and c2. Integral over c1 is just I. And the integral over c2, we evaluate like this. So it's f of z dz. So z here is x e to the 2 pi I. Notice that we need the 2 pi because we're not really at 0 here. We haven't wrapped quite around. We're just taking the limit as this becomes very small. So we're very close to 0, but actually we're very close to 2 pi. We're like 1.99999 pi, or whatever I. So that's why this is a 2 pi I, not a 0 here. So we plug this in. We have the integral from infinity to 0, because we're going this way, of x e to the 2 pi I square root over this thing times ln of this, and the dz gives us a dx e to the 2 pi I. But this, of course, is just 1, so we don't care about it. So when you take the square root of e to the 2 pi I, we'll get e to the pi I. That's just negative 1, so that's where this negative comes from. We use the log properties again to separate these two terms. And then we have this integral here. The negative cancels the inverted integrands, or the limits of integration, I mean. And this gives you the original integral I. And the second one gives you 2 pi I c. Well, let's see. Well, this integral here, 0 to infinity of root x over 1 plus x squared, that's some number, some real number, right? There's no funky stuff going on here. So that's just some number c. I'm just calling it c, and you'll see why in a minute. Because since we said that the whole integral, all four integrals, sum to 2I plus 2 pi I c, then you can find I because we're going to take the real part of the sum of the residues. That's just going to be I, because this is just imaginary completely. You don't need to evaluate c. Even though the question said we might have to, we actually don't. So the two residues are at I and at minus I. And they're pretty easy to find. We just factor the polynomial denominator like this. And then we plug in for whichever one is not 0. So if c is I, then this is 0. So we plug in I plus I, square root of I, natural log of e to the I pi over 2, because that's I. And then we have this, pi over 4, e to the I pi over 4. Then we have negative I, so the negative I comes into this one that I crossed out. So we have negative 2I, you have the square root of I over here, you have the natural log of 3 pi I over 2. And notice that the 3 pi over 2 actually is important, because when we were doing this integral before, we defined this argument as 2 pi I. So we can't use minus pi over 2. We have to use positive 3 pi I over 2. So that's why this is here. And that gives us 3 pi over 4, e to the 3 pi over 4 negative. Notice that the i's are canceling here. This I is going to cancel this I. So 2 pi I times the sum of the residues, therefore, is pi squared over 2, 1 plus 2i. You can evaluate that yourself. And this, we said, is equal to 2i plus 2 pi I c. So I, of course, must be equal to, because this is real, must be pi squared root 2 over 2, because there's 2 of the i's. And that's exactly what we wanted. And actually notice that we can find c as well. Take the 2i pi squared over 2 term, divide by 2 pi I, you get pi over the square root of 2. It's this integral c, this square root integral we had to do here. And if you put that into Wolfram alpha, you can see that actually that is correct. So isn't that cool? We were able to evaluate both of these integrals without doing the second contour integration. So I hope you guys thought that was instructive, and that's it.